So this is chapter 21. We're learning about something called the electric potential. Sometimes it's called the voltage. Sometimes it's called the V field. It has many different names. Sorry. So what we want to do, we want to understand electric potential energy and electric potential. And we're going to use them in conservation of energy problems. We'll find and use the electric potential of point charges, charged spheres, and parallel plate capacitors. We're not going to really worry about that too much. We'll understand the connection between potential and field. That's crucial. And we'll talk about capacitors and dielectrics. All right, so the next slide is a very famous, I don't know if it's a painting or a drawing, so I'll just say painting. Very famous painting. And this works really neat, really well when we have a whole classroom of students, but oh well. So as soon as I show that next slide, immediately I want you to yell out what you see. So basically what we're interested in is the color and the object, what you see and what color it is. All right, so ready? 1, 2, 3, go! So shout it out. Okay, now some people, when they see this thing, they see these white birds. Some people, on the other hand, see these black birds. Now, and so when we do this with a classroom, it's usually like 50-50 or so. But obviously there are white birds in that painting and there's black birds. And so why am I showing you this? Well, there may be two ways of looking at the same thing. And you'll understand that as we progress. All right, so it's a fact of nature that electrical charge exists. And there's positive charge and there's negative charge. And it's up to us, human beings, to develop a mathematical theory about charge. And of course, that theory has to explain everything there is to know, all the observations about charge, and it has to be able to be tested, right? So it has to be able, because what good is a theory if you can't test it, right? And so that's why you want a mathematical theory, because you want to be able to test it. Now, one theory that we've discussed in the past, last week, or last chapter, I guess, is the idea of an electric field. Well, can we come up with a different way of looking at it? Well, of course we can, all right? And so that's what this chapter is about. It's just a different way of looking at electric charge. Okay, so far we've discussed electric fields. And charges create electric fields. And electric fields are related to the electric force via this equation. The E field equals the force measured between the charge that created the E field and the probe charge. And then since we don't want the E field to depend on the probe charge, we divide by it. Okay, and as we said last time, Maxwell's equations, which describe everything there is to know about electricity and magnetism, classically anyway, are in terms of these fields, right? So the fields are really important. Well, there's another way of looking at this, charges, and that's what we want to talk about. And actually, what we're going to talk about this chapter is much more useful or practical than this electric field way of looking at things. All right, so again, charges create an electric field. Well, guess what? Charges also create something called an electric potential, which is also called potential, which is also called voltage, which is also called a V field for voltage field. Sorry, I have 4 names for the same thing, okay? All right, so now what's so great about this? Well, the electric potential isn't related to a force, it's related to electric potential energy. And again, look at electric potential energy, that's a scalar, right? And so this is also a scalar. So here, you have vectors. Well, here you have scalars. Okay, now, this is the definition, as I said, of electric field. E equals F over Q0, right? So what I want you to do is just kind of, use the thought process that we used to come up with this equation and come up with something here, right? Again, electric field is related to force. Electric potential is related to potential energy. So what do you think would be a good equation for electric potential? Using something like that. Well, hopefully, you'll come up with this, right? I mean, here we had E equals F divided by the probe because we don't want this to depend on the probe. I said that the potential is related to potential energy. So this is the potential, V, that's why they call it a V field. So V equals electrical potential energy divided by the probe because we don't want this to depend on the probe, okay? So the potential or the voltage or the V field is the potential energy divided by the probe charge. All right? Okay, so so V equals UE over Q. So later on we're going to use this a lot. We're going to use UE equals QV, right? So that's important, but that's important too. They're both important, and we'll use them all the time. Okay, so let's explain it. Let's explain it. So here is a charge, right? Q. The charge is Q. Now, what we do is we put this little probe charge in the vicinity. And remember, this is small, so it doesn't really have any effect on this thing, right? So small is necessary, okay? Now, with the E field, I said, as soon as we put the probe, I said, what does the probe charge feel? And we said, force. Well, now we're not going to do that because we want a scalar, all right? So again, here's this big Q, and here's this little fellow, right? I'm not going to say what it feels. I'm going to say, what does it have, right? What does it have? Once you put this probe charge in the vicinity of this, what does it have? Electrical potential energy, right? I mean, when I take this and let's say it was on the floor, and I raise it, what does it have? It has gravitational potential energy. Well, if I take a probe charge out of my back pocket and stick it here in the vicinity of this, what does it get? What does it have? It has electrical potential energy. All right, and what does that electrical potential energy depend on? Well, it depends on the charges. It depends on the distance, okay? And so how we're going to describe this, we're going to describe it as an interaction between, well, it's a scalar, right? There's no vectors here, okay? So it's an interaction between this and the scalar potential or V field or whatever you want to call it created by this charge, right? Okay, that's really it. All right, and again, the potential or V field, I like V field because, like last chapter was E field, right? Electric field. So I like to call this a V field. I mean, they use V, right? So why not just call it a V field, right? Anyway, V field, right? So this creates the V field, and this is defined to be the potential energy, which is an interaction between these two charges divided by that. Okay. All right. Now let's see the units. So the V field equals potential energy over charge. So from physics 105, the unit for energy is joule. The unit for charge is coulomb. So we'd be perfectly happy just calling it a joule per coulomb, but got to call it for something else. Volt, right? Volt, V for volt, which you're familiar with. So that's why some people call it the voltage, because it's measured in volts. All right. Now, why is this useful? Why do we have to? What's wrong with just using E field? Why do we have to come up with a completely new way of looking at things? Well, come on, think of it. What's the unit? Volts. Now, where have you heard of volts before? Batteries, right? Batteries. I mean, what's the unit of E field? Newtons per coulomb. Have you ever gone to Ace Hardware and bought anything that has units of newtons per coulomb? No. But you've bought batteries before, right? And volts. So basically, you can measure this V field with a voltmeter. Yay! All right? So it's just useful, okay? All right, so let's kind of just summarize. So the viewpoint we had last chapter, we said that a charge creates an electric field. We measure the strength of that electric field by approaching it with a probe. The probe feels a force. And again, forces, in fields are vectors, right? So here's the E field, the force divided by the probe. So that's one way of looking at it. That's the definition. But we can also say, if we have an E field, some external E field, we stick a charge in it, it's going to feel a force given by this. This is a really important equation, by the way. We're going to use that a lot. So that's one way of looking at it. The second way of looking at it is we say this thing creates a V field, a potential field, a scalar potential field. How do you measure it? You put a probe near it. The probe has potential energy, just like this thing has gravitational potential energy. You put a probe near this, and it has electrical potential energy. Energy is a scalar, right? It's not a force. So we have scalars. So the definition is the V field, or the voltage, or the potential, is the potential energy that this and the probe have, but then you can divide by the probe because you don't want this to depend on the probe. So that's the definition, but you can also use that. We'll use that a lot. And again, you can measure this with this. I mean, we never talked about how to measure that, right? Ever heard of an E field meter? Probably not, because it doesn't exist, right? So this is wonderful. I mean, it's using Maxwell's equations, but this is practical. Okay, now, so both of these describe charge. So they describe the same thing, just in a different way. So do you think that this should be related to this? Well, of course! And we'll talk about that later. All right, now, we want to concentrate on this now. So in order to understand this, we need to talk about electric potential energy. Electric potential energy. Oh, it's time to stop already. All right, let's quit. And that was fast.